Greetings. I am Benjamin Bacon, the owner of Plain Space Design, and in this video I am going to describe a unique design of a propulsion system for space use in the context of space commerce. This propulsion system has what I have called an embarrassment of riches. It is said because in the context of the space travel that we know today, this space propulsion system can alter the balance between the things that we can do and the difficulties that we face in trying to achieve the things that we want to do. These riches are as listed here, starting with the weight, which is one of the biggest problems that space travel faces. The weight restraints for this spacecraft and these designs for interplanetary travel and for planetary travel are very, very relaxed. That means that the fuel weight limits are not applicable in the designs around this propulsion system. The propellant fuel is not the item that is consumed. The only consumable item is electricity, which is also a renewable item. The propulsion system is also contained inside of the spacecraft in some designs, and in that case it is fully accessible by the crew members. They can see it, they can touch it, they can access it, and they can repair it, all without exposing themselves to the dangers of the space environment. Further, the complexity of the propulsion system is reduced drastically, and that means that it can be repaired while in flight if there is only a minor problem. Also, it can be restarted, so it can be stopped in a drifter mode and maybe a major repair can be made and then the propulsion system restarted. And conceptually, we can achieve some very high velocity travel. In fact, conceptually, it is possible to achieve fractions of the speed of light, and therefore we may be able to begin to explore interstellar space and make interstellar journeys to nearby stars. And the most exciting part, the greatest riches of all, is that there are many opportunities for invention and discovery in this new propulsion field. The theory of propulsion within which we will be working is new, and all of the engineering will require and also enable us to create new devices, new ways of doing things. So there is great opportunity in this propulsion system design. In this video, I will present to you a proof of concept. And the structure of this proof of concept will be an idealized paper and pencil simulation of the way the propulsion method works. And we will use this proof of concept to show what the propulsion method is, and we will validate that it works according to known physical principles. So there will be no need to apply magic or futuristic imaginary devices to get this propulsion concept off the ground. So in the demonstration that will follow, I would want you to pay attention to what happens to the center of mass of the system. The simulation is set up as thus. There are two free unit masses separated by a unit space, and these unit masses can be pulled together or pushed apart by a reversible force. Additionally, there is a fluid mass that can be transferred between the unit masses, changing their relative weight and inertia, and consequently, it would also change the location of the center of mass of the system. So all of the assumptions in this simulation are realizable. Here we have the Excel spreadsheet layout in which the proof of concept was simulated. Notice that there are rows for position of each of the masses and the magnitude of each of the masses. Each mass is like a tank. In one mass, the one that is shaded, there is a fluid. So the shaded color is the fluid mass. This fluid mass is transferable from one tank to the other. Below each mass is listed its position and the magnitude of that mass. So let's examine the initial state of the system. We have mass 1 located at position 0, and it has a magnitude of 1 mass unit. Mass 2 is located at position 2 initially, and its initial mass magnitude is 2 unit. So this is the datum. Mass 1 equals 1, its position is at 0. Mass 2 equals 2, and its position is at 2. From this datum, we calculate the center of mass in the x direction. The center of mass formula, m1 times x1 plus m2 times x2 divided by the sum of the masses. We plug in the datum and calculate the position of the center of mass of the system. So the initial center of mass position is at 4/3. Here we have a table that gives the state number, which is the step number equivalent to time steps, and the center of mass at that time step, or state number. So the initial state is state 0, and the center of mass position in state 0 is 4/3. When I advance this video, pay attention to this simulation area, and you'll see an animation of the changes. And then we will go and discuss the state change that occurred down to the state table. Prepare, ready, now. Now see, we have applied a force to pull mass 1 to mass 2. And it has moved 1 space unit. So this mass is now at position 1, but it still has magnitude 1. So the state change 1, pull mass 1 to mass 2, change the position of mass 1, giving us the state m1 equals 1, and the position of 1 is 1 now. Mass 2 has a magnitude of 2 at position 2. Plug this data into the center of mass formula, and now we have a new center of mass at state number 1 of 5/3. Advance state. Now notice that mass 1 is shaded. That means that the fluid is now inside of its tank. Even though its position has remained the same and the position of mass 2 has remained the same, mass 1 now has 2 mass units on it. State change 2 then is transfer 1 unit of mass from mass 2 to mass 1, changing the relative mass distribution. This is called a mass transfer, or MX for short. So the state of the system is mass 1 has 2 units, its position is at 1, and mass 2 has 1 unit, its position is at 2. Plug the data into the center of mass formula, and the new position of the center of mass at state number 2 is 4/3. Advance the simulation to state number 3, and now we have applied a force again, and this force separates the two masses, pushing them apart. Push mass 2 away from mass 1 and change the position of mass 2. So the change in the system was here, the position of mass 2. Mass 2 is now at position 3, but it still has the same mass. There was no change in the state of mass 1. So M1 equals 2, and its position is 1. M2 has 1 mass unit, and its position is 3. Plug the data into the center of mass formula, and we come up with state number 3, being that the center of mass is at position 5/3. Now we will move faster and advance the simulation one step at a time. Going to state 4. Notice that in state 4, we have transferred the mass, the fluid mass, back to mass number 2. So it now has a mass of 2 units. Transfer 1 unit of mass from mass 1 to mass 2, changing the relative mass distribution again. Another mass transfer has occurred. This is the datum. This is plugging it into the center of mass formula. We now get a position of the center of mass in state 4 of 7/3. State change 5. We now pull mass 1 to mass 2 again, eliminating the space between them. So the position of mass 1 has changed to 2. X1 equals 2. All other things remaining the same. Plug the data into the center of mass formula, and at state 5, this position of the center of mass is 8/3. Advance to state 6. And here, after state change 6, we have a mass transfer from mass 2 to mass 1. This provides us with the following data. We plug that data into the center of mass formula, and we get the result that the center of mass position at state 6 is 7/3. We use the force to push mass 2 away from mass 1. So the position of mass 2 has changed to 4. Plug the data into the center of mass formula, and the position of the center of mass at state number 7 is 8/3. Advance the simulation. And now we have a mass transfer from mass 1 to mass 2. current data is here. Plug that data into the center of mass formula, so we get the result that after state change 8, it is 10/3. We have pulled mass 1 to mass 2, changing the position of mass 1. This is the change in the data. Plug it into the center of mass formula so that at state 9, we have the center of mass being at position 11/3. Mass transfer from mass 2 to mass 1. Mass 1 is now shaded. This is the data plugged into the center of mass formula so that state number 10 has the center of mass position changing to 10/3. Advance to state 11. We use the force to push mass 2 away from mass 1. The data, the center of mass formula, and in the table, state 11, the position of the center of mass is 11/3. So the effect of the state changes applied to the system will show that the center of mass translates to a new position in the positive x direction from 4/3 to 11/3 in 11 steps or 11 state changes, as shown here in the table. Now all of these events that were applied to prove this concept in this simulation are things that can be achieved in the real world. There were no extraordinary effects applied except the effect of idealization. And even though it is possible to have one mass remain stationary while a mutual force is applied between two masses, that would require something outside of the context of this design discussion. In reality, when a mutual force is applied between two masses, both masses move, but they move relative to their inertia. And that is why the fluid mass is changed, to redistribute the inertia within the system and still achieve with varying degrees of efficiency this same type of translation, not in this idealized fashion, but in a fraction of it. So if we try to bring this design into the real world, that is, realize the design, we will see some of the problems and challenges that were present while the concept was being developed, and some of the problems and challenges that have already been overcome. One of them was mass transfer. The fluid mass has to move from one tank to another. That problem has been solved. Push and pull forces, pushing masses together, pulling them apart, or pulling them together and pushing them apart, however you want to look at it. Power source is another problem that had to be designed out of. So we needed an effective power source. Then there was the problem of spacecraft and propulsion system integration. The propulsion system is one thing, the spacecraft that it goes into is another thing, and we have to make these two things fit together. Then there was the problem of how to launch this spacecraft into space. It does not have the ability to lift its own weight under the influence of gravity. However, when it becomes weightless, then it is in its ideal environment for operation, that is, the weightlessness of space. Then you see that there are several accelerations and changes of direction that may happen. So there is the problem of figuring out how to smooth that ride if we were to consider this as a human usable propulsion system or a human rated system. So in the realization of the design, some of the problems have already been solved. One of them is the problem of designing a method of transferring the mass from one module to the other. There turned out to be a lot of ways that can be done, but we wanted to get the fastest mass change that we could have possibly achieved, because the faster the inertia is redistributed, the faster or the more distance the craft can travel in an amount of time. In other words, we're speaking velocity. And there were many clever ways of doing this, but one of them, or two of them, or three of them are better than the others. So this part of the design had to be optimized, and some optimization has been achieved. Also, in realizing the design, we would have to solve the problem of finding a method of creating push and pull forces between the masses. These are mutual forces, and there are many ways to apply reciprocating force to the system. But we worked under the constraint that we wanted to achieve the greatest force with the least energy usage. Because even though it is a renewable energy source, out in space, electricity is come by through difficult means. So you don't want to waste it. You want to use your electricity for propulsion as efficiently as possible. And ultimately, we settled upon a magnetic force system. However, in some mission designs, the magnetic force system is not the best. So that is a mission design parameter. It is affected greatly by what the propulsion system must do. So magnetic force system is not the only system, but it was the first that we chose to design around. Realization of the design also had a problem of finding a power source for this propulsion system. And since it is an electrical propulsion system, we know that that problem is never fully solved, because we are still working on finding better electrical power sources. But we know that there are the nuclear sources and the solar electric power systems that can be used in space right now. Then there are fuel cells. All three of these are feasible and will work in some missions scenarios with this propulsion system. And then we solved the problem of integrating the propulsion system into a standard spacecraft structure. So the requirement that the modules of the spacecraft or the masses be free masses and still be integrated into a single system challenged the design activity greatly. We require that there be no interaction between the unit within a certain mean free space. And so there are many different mechanical arrangements and structural arrangements that will accommodate this requirement. And all of these are realizable with current technology. Then there is the problem of getting this spacecraft off of the Earth or off of a planet's surface into space. The propulsion that it produces is not good enough to do that on its own. So it can be launched by conventional space systems and then assembled in space. This is a currently practicable activity. And then there are some challenges whereby we would have to try to smooth out the ride. And of course, this is the one that is the most difficult to do, because by its very nature, there are accelerations going to and fro as the masses change direction in response to the changing of the polarity of the force, pushing them apart, pulling them together. And these accelerations and lurches need to be minimized. Of course, there are systems that we can apply: damper systems, shock absorbing systems, spring systems, that can all be applied, but they limit in their application the durability of the system and how reliable it will be after long periods of usage. However, this obstacle can be overcome by some genius who is very well versed in mechanical system design. So the conclusion is that this propulsion system design has some implications for future space travel, and that is that it will solve the problem of traveling in space and not being able to take a lot of supplies and hardware with you. The fortunate fact, the great riches of this propulsion system is that the more the mass, the greater the efficiency. And in the future, as its design develops, that will become very clear to everyone. Then, if we are able to put some of our best available talent to the task of developing this propulsion system, then it will probably even exceed our expectations. And we will no longer have a problem of getting into deep space and beyond in very fast times. So thank you for watching this video presentation. And as a reward for staying the course, you will get this special slide.